Okay, I mean, we spent time doing this Chapter 8 review in class, and we actually went over it as well. Well, I'm doing this before we're actually going over it, but I'm assuming we're going to be going over this in class together. But if there's something you missed, or if there's something that was incorrect, or whatever else, I'll go over it here, saving using the calculator, so we'll see how I do. So our first thing here is we have to complete this table, show calculations neatly in the table. This is all about your ability to say, even without a drawing, even with some limited number of, or with some limited amount of information, how can I work from that to getting everything about this thing? Remember, all these are regular polygons. That's our assumption here. So that's what we're playing with. Well, actually, I'm sorry, not all of them are, but they're saying if it's regular, then what would we have? So before I even start this, we know that the sum of the measures of the exterior angles is always 360 degrees. So I'm just going to spill that out for all these. This will help you as you go along. And I'm actually going to show you with the first example how you can figure all these things out in two different ways. First, I'll go with what I consider to be, I guess, the easier way. Finding the measure of each exterior angle in a polygon. Let me first, even before I do that, let me give you an example of a polygon. Let's just start with the Pentagon here. Exterior angles are these guys. Okay? Like those right there. Okay, and they add up to 360 degrees. They always do. That's what we're talking about here. And there will be 5 of them in a pentagon, much like there will be 24 of them in a 24-sided polygon. So when you want to find the measure of each degree, like right here, you take 360 and divide. So 360 divided by 5 gives you, in that case, would be 72 degrees each. So those will be 72. Now, I don't think we have a 5-sided shape in one of these, or it's not given to us. But basically, so that's how that works. All these are 72 degrees. So to find the measure of each exterior angle, here you'd be 360 divided by 24. 360 divided by 24 is 15. So each exterior angle in a 24-sided shape is 15 degrees. What this helps you do, I'm going back to the Pentagon for a second, is this helps you find the measure of each interior angle in a regular polygon. So the interior angles would be these guys on the inside. So if you look at that, these guys are always supplementary. This plus this is 180. So this, I could call x right now. This plus 15 is 180. So if I subtract 15 from 180, I'll get my answer, which is 165. So these are all 165 degrees. Now the sum of the measure of the interior angles is taking each interior angle and adding them all up. And in this case, in a 24-sided shape, or better yet, a 24-angled shape, if all 24 of them are 165 degrees, you do 165 times 24, which ends up being 3,960. Okay. Now there's an alternate way to do this entire thing for this one. Okay. Looking at the Pentagon one more time, a 5-sided shape can be divided into 3 triangles, all which connect together, forming angles. I can choose to do it that way. There are a bunch of different ways you can do it. But here's 1 triangle, 2 triangles, 3 triangles. 3 triangles form to make 5 sides. In case you were curious, in an 8-sided shape, I'd be doing the same thing, where I have 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6 triangles in an 8-sided shape, etc., etc., etc. So you can tell there are 2 less triangles than there are sides. So in a 3-sided shape, in a triangle, there's only 1 triangle. And as you know, in a quadrilateral, there are 2 triangles, etc. So there are always 2 less triangles to number of sides. So I could even put triangles equals n minus 2. Number of sides minus 2 is number of triangles in your shape. Super important to understand for this concept. In a 24-sided polygon, there are 22 triangles. Now every triangle has an angle sum of 180 degrees. So the entire polygon is the sum of your degrees of your triangles. So in a pentagon, that's 540 degrees. In a quadrilateral, that's 360 degrees. In an octagon, that's whatever 180 times 6 is. I think 1440. I'm sorry, that's not even close. That's it's 1080. 1080. Okay. So in 24-sided shape, it'll be number of triangles times 180. So there are 22 triangles times 180. We use the formula D, the sum here, D of the angles is 180 times n minus 2. And that's where that comes from. Number of triangles is number of sides minus 2. So 22 triangles multiplied by 180 to get the entire sum of all of them. So 22 times 180, you guessed it, is 3960. If I wanted to find the measure of each interior angle of a 24-sided shape, I take the total number, I take the sum of my interior angles, and then I divide by the number of sides, 24, or the number of angles, better yet, and you get 165. When you have 165 here for your interior angles, your exterior angles can be found because these are supplementary. So 165 plus, if we call that x, is 180. You subtract 165 from 180, you get 15. And then you can double, triple check this if you need to. 15 times 24 is 360. So there are two different ways that I went about this problem. Okay, so I want you to understand both ways. These other ones I'm going to go through much more quickly. I just wanted to get that all out of the way in the first bit. Okay, so this will be one where it's like, uh-oh, I don't know the number of sides, so I can't find exterior angles. So this time you're going to have to use that D equals 180 times n minus 2 to kind of get a jump start. What this says is I have the angle sum right here, the interior angle sum, 50, 40. I need to get the number of sides. To get the number of sides, I just want to know how many triangles there are in this. If I divide both sides by 180, like this, then I'll figure out how many triangles there are in it. And the number of triangles would then be 28. You do 50, 40 divided by 180, you get 28 triangles. Plus 2, that gives you 30 sides in your polygon. Okay, and again, the explanation of triangles and stuff is above. So if you don't get that, make sure you do, as you work on that. Okay? So you get 30 there. After that, you can work on the measure of interior, well, actually you can do two different ways. Let's do exterior angles here. 360 divided by 30 gets you 12. 12 degrees for each exterior angle. And again, if you have a question on exterior angles, we talked about it up above. And then this must be 168 degrees. It's 12 plus 168 is 180. These have to be supplementary. To double check that, do 50, 40. 5,040 degrees divided by 30, you'll get 168 over here. I'm sorry, did I say 30? I'm not sure what I said. 30 sides, hopefully. Okay, measure of each interior angle is 171 degrees. That means measure of each exterior angle is 9. To find all the rest here, I can find the number of sides if I know the measure of each exterior angle. If I have 9-degree exterior angles, 9 plus 9 plus 9 plus 9 plus etc., how many of them do you have to add up to get 360? So, algebraically speaking, it would be 9x equals 360, like that. 9 times the number of sides, 9 degrees times the number of sides equals 360 degrees. So how many sides are there? Divide both sides by 9, and you'll get x equals 40. So this is a 40-sided shape. Okay. Now in a 40-sided shape, or 40-angled shape, with 171-degree interior angles, the sum of your exterior angles is 171 added together 40 times. So 171 times 40 is 6,840 degrees. That's your angle sum, interior angle sum. And finally, the last one here. You're given the exterior angle measure. You can get the number of sides immediately. 20 plus 20, x number of times equals 360. So how many sides are there? Well, there are 18, because 360 divided by 20 equals 18. Also, 20 degrees gives you measure of the interior angles. 180 minus 20 is 160. 160 degrees there. 18 times 160 degrees gives you interior angle sum, because there are 18 of these 160-degree angles. That's 2,880 degrees. So there you go. That fills out the table for number 1. And Hopefully that first one kind of covered how you can do this multiple ways sometimes once you get some bits of information, especially number of sides. That really starts to help. Get these out of the way so you're not looking at them. Okay, number 2, a regular decagon's inscribed in a circle. The radius of the circle is 15 centimeters. So you can see the circle actually on the outside. Excuse me. And actually, I'm going to make it a different color. Let's go with that. Let's make it red. Let's hope the center is right in the middle. Pretty close, right? There you go. There's your circle. And it has a radius. Make it red. Let's make it dotted. Let's have some fun with it. Now, radius of the circle. Notice that the radius of the circle is also the same as the radius of the polygon. If I go out here to the apothem of my polygon, you'll see it's shorter than the circle's radius. So I'm going to draw it out to something that gives me both the radius of the polygon and the circle. So when it meets at the polygon's radius. I could have probably done that a little better. Let's try it again. Out right there. Okay. That is a radius of the circle, which is also a radius of the polygon, and that is 15. Go 15 centimeters. Okay, find the area and circumference of the circle. So the circumference, let's do area first. Area of a circle is pi r squared. Pi times squaring the radius. The radius is 15. So your area, if I take 15 and square it, and multiply that by pi, I get 225 pi square centimeters. If you want an approximation of that, because this thing did actually ask you to round all decimals to 2 decimal places. That's if you use decimals. 225 times pi is about 706.86 square centimeters. Ran out of room. Okay, so that's the area. That's the fill-in. Shaded. That's the fill-in of the entire circle. The circumference is 2 pi r. So twice the radius. Like this entire thing, the diameter times pi. If you multiply that by pi, you'll get circumference. That's the ratio between circumference and diameter. So 2 times 15 is 30. So circumference is 30 pi centimeters. Remember, it's a length. It's not an area. Or it's approximately 94.25 centimeters. Okay. So either or. Find the area and perimeter of the regular decagon. Okay, now the decagon is the inside, and perimeter you can only find if you had the length of each side, which we don't. We have the radius, and you're saying, well, is that enough? Can we just use that? And do we have enough information if we do that? Well, we do, but we have to find it. So I'm going to go ahead and draw this apothem here. Okay, the apothem's the crucial part of this in so many ways. Number 1, this thing's a perpendicular bisector. Which means it's not only right angle, which creates a right triangle, it divides these into 2 congruent parts. So here I'm looking at a right triangle. My hypotenuse is 15. Now I don't know what these two things are, and I need to find them. I'll call this A and I'll call this B. A for apothem, B for, well, kind of for base if you want. The A squared plus B squared is C squared, which would be nice, but I don't have any information yet. Let's go and find one of these sides using trigonometry. And check this out. We have to use trigonometry because this is not a special triangle. In a decagon, I'm going to go ahead and draw 2 more radii to form a new central angle here. Let's just use these right here. Check out these 2 radii. They form this central angle. Now, all the central angles are congruent because this is a regular decagon. Right? So here's a central angle. And all central angles add up to 360. So this one plus this one, etc. There are 10 of them. So just like exterior angles, I'm going to say central angle equals 360 over 10, which equals 36 degrees. So each central angle is 36. Now this is not a central angle. This is half of a central angle. This is going from radius to apothem. If I went radius to radius like that, this would be 36 degrees. So if that's 36 degrees, this apothem bisects the angle. It creates 2 congruent angles here. So this is 18 degrees. It's half of 36. Make it very skinny this time. 18 degrees. I should probably write like that more often. this is 18. If that's 18, and this is, I don't want to make a mistake, it's 72. I'm going to use the 18 just in case your math screws up. You don't ever want to screw that up with it. So 18 degrees and 72 degrees. Now we actually have degree measures, and now we can actually find lengths as we do this. Okay. I'm going to go ahead and say, well, we need to find this apothem for sure. Okay, so let's go and find both. Let's say the A. Okay, if we're going to find A, let's use 18 degrees. Let's say the cosine of 18 degrees is the adjacent side over the hypotenuse. So cosine 18 is A over 15. You want to then multiply both sides by 15, you'll get A equals 15 times the cosine of 18 degrees. I'm going to do this in two separate ways. I'm going to give you what this actual number is. Actually, I don't know what the actual number is. Because I wrote it on my paper and I waited till the end. Do you have a calculator by me? Hold on a sec. Okay, I'm back. I found a calculator, and let's do 15 times cosine. Okay, I'm getting 14.27 centimeters. Okay. Now make sure your number is reasonable. This should be really close to 15. You can see how tall and skinny it is, just like this one. It shouldn't be greater than 15, and it should be pretty close. So that looks like I entered my number correctly. Now B, if I used, let's say I used 18 degrees again. B is opposite of 18, and I can use 15 centimeters again. So sine of 18 degrees equals B over 15. So B is 15 times the sine of 18 degrees. So I use that in my calculator. I get 38. Oh, wait. That's not right. Did I do... Try that again. 15 times 18 sine. There we go. B is about 4.64. So you can tell, like, when I just did that, I made a mistake somewhere when I was entering that. I noticed because it was like 30 something. I shouldn't get a number like that. It should be a lot smaller. So B is about 4.64. This helps me find the perimeter. Now what I'm going to do, really, and what you should do, and this is what I was talking about, and I'm going to waste space down here, is this is an exact number. This is an approximation. If I take this and multiply it by 2, then I'll get the length of this part right here. Okay. If I take B and multiply it by 2, then I'll get the length of one entire side, because B is only half a side. So make sure you keep that in mind when you're doing this right triangle business. B is only half a side, multiply by 2, I get the thing. Thing is, if I multiply this by 2, this is an approximation. If I multiply this by 2, it's an exact value. So when I do all this, I really want to figure out the perimeter by using exact values. If I do this, multiply this by 2, then multiply it by 10, because I need to find the perimeter of the entire thing, this will be an approximate number. This will be an exact number, until I need to round off. So when I do the perimeter here, and I'm always going to give you rounded answers to what's most appropriate here, the perimeter will be 10, this number of sides, times 2, because remember, I have to multiply this by 2 to get the length of one actual side, so just making sure you get that, times 15 times the sine of 18 degrees. So although the 15 times the sine of 18 degrees is about 4.64, I'm going to use what the calculator gives me as more of an actual number, and then I'll multiply all this. And then P becomes an approximately 92.71 centimeters. It's 92.705, which rounds up. Check this out. If I take 4.64 and multiply it by 2, I'm doing this on the calculator, multiply it by 10, I'm going to get 92.8. Okay? Not much different, but it is different. Because now I'm going to multiply this by my apothem, which I got over here. Okay? And that's also a rounded answer too. So if I really wanted to find the actual area... now, by the way, this is a good answer for your perimeter, 92.71. This technically would not be the same number. But my apothem is 1/2 AP. So I should say It's 1/2 A, which is 15, times cosine 18, times P, which is 10, times 2, times 15 sine of 18. This will give me as exact of a number as I could possibly get when I do this, instead of using my rounded numbers. I hope that makes sense as far as why I'm using these weird numbers to get my entire thing, because I'll show you what the difference is again between this and the approximated number. I'm typing on my calculator here. 661.26. So A is 661 point, it's 258, so 26 square centimeters. Okay, so I got that as my area of my decagon. Now again, if I rounded it, it would be A equals 1/2 14.27, my apothem, times, in fact, let's use this rounded number even, just to be saying this is why we don't use a rounded number of a rounded number when we do this. Times 92.8, so that's 0.5, so 1/2 times 14.27 times 92.8. Okay, so I get 662.128, 0.13. Because we're rounding. Okay, so again, number's not much different, but shoot, it is different. It's a whole square centimeter different. And again, doesn't seem like much, but when you're talking about, like, remember when we did our Pentagon thing, those values are in the hundreds of thousands. So now when you do a rounded number like that, it's not 1 square foot off, it's 100 square feet off. So those become a big difference. And when you do more calculations, so on and so forth, you'll see why those numbers keep changing. You don't want to use rounded numbers as you go. So ignore doing that one. Go and do that one. So we found apothem and perimeter, area and perimeter of the decagon. And double check this number. Does this number make sense? Is it less than the area of my circle? Look at this. The circle's outside the decagon. The decagon has space that's not being used. So it should be less. And this is why it's good to sometimes round this, because now you know what your number looks like. It's a little over 700. The area of your decagon is under 700. So, and it's not much less than 700. So yeah, that makes sense. It looks like these numbers are right. If you get a number of 800 here to 700 here, you know something's wrong. Either one of them, two of them, or both of them. The area of my decagon cannot be bigger than the area of my circle, because the circle takes up more space. So, you know, double check though, see if that's logical. Even this one's logical. It's close to a good answer. But yeah. Okay. Draw AC and BC. Find the area of sector ACB. Okay. AC is from here to here. Let's use a different color. AC. Here's BC. And we define the area of the sector. Now the sector is the entire thing for the circle. So it's the area of this whole guy right here. Okay, to find the area of this, what we're going to do is we're going to take the area of our circle, which, again, I'm going to use the exact one first in my calculations. I know this is our number, but it's approximated. I can take this area, and I'm going to find what percentage of my circle is this central angle. So, central angle from A to B here, what is it? And we'll figure that out by saying, well, all of these from the radii, if you still have them figured out, these are all 36 degrees. So 36 plus 36 plus 36, or 36 times 3. So that's 108. Okay, so we're going to set up a proportion as we do this. And I'm going to go back up there in a second. But we get 108 degrees out of a total of 360 degrees. That's the fraction of my circle that I'm looking at. 108 degrees out of all 360 is equivalent to the area of the sector out of the area of the entire circle. Okay, see if that makes sense again. This is 108 degrees, I know, because all my central angles are 36, and I'm taking 3 central angles here. 108 out of the entire 360 is the same as the area of this sector out of the area of the entire circle. Now sectors apply to circles, not polygons. I suppose. That's what we said by definition, so make sure you use that. So that's why I set up this proportion here. 108 over 360 can be reduced to 3 over 10. Okay. Even if you didn't know this was 108, you can know this is 3 over 10 because if this was a clean-looking decagon, again, you can see that there are 10 radii that are formed. This is 3, 1, 2, 3 out of 4, 5, 6, 7, 8, 9, 10. So 3 out of 10 of them are being occupied. That reduces there anyway. Equals x over 225 pi. Don't forget the pi if you're going to use that. Multiply, cross multiply here. We'll get 10x equals 675 pi. Divide by 10, and x is 67.5 pi, which is a strange square centimeters, which is a strange value. I don't like decimal and pi together, so this is a case where I wouldn't mind rounding in the end anyway. So the area of the sector, when multiplied by pi, is about, let's approximate that, 212.06 square centimeters. Okay. So either this or that. Either's appropriate. But, see if that number looks right. Make sure that the number's definitely less than 700 when you do the whole thing, so, or less than 225 pi. Yes, that's the area of the sector there. Okay, a regular 12gon, or better yet, a dodecagon, I guess not better yet, but that is the name of it, has a side length of 18 centimeters. Now we're looking at the sides. This is 18, as this is 18 because it's regular. A sip of water here, 1 second. Okay, we're going to find the area of the entire thingy. We're going to show all work as we do it, as they ask us to. Let's start with a centerpiece. Let's give a center. This center can help us form radii and apothems. I just need one apothem really and one radius. Straight line tool. Let's make it thinner. I'll use black all around here. I'm drawing an apothem and I'm drawing a radius. Now remember, this is a 12-sided shape. So the first thing you have to do is, look, they don't give you any angle measures. It's up to you to figure that out. You have to determine it. Now you can. Look, we did it up here in the very beginning. You know how to get measures of interior angles and such with a 12-sided shape. And just so you know, literally just for good measure, the measure of an exterior angle in a polygon with number sides is the same as the measure of the central angles. So in a 24-sided shape, if an exterior angle measures 15 degrees, so are the central angles. Just like we did here, these were 36 degrees. An exterior angle also measures 36 degrees. That right there is also 36. Okay. Another way to notice that is this is 72. So on this side, this is 72. These add to 144. 180 minus 144 is 36. So that's 36. So again, jumping all around. Here are different ways you can look at these angles and everything else. So a central angle would be the entire thing. It would be, whoa. It would be that and that. So the central angle is taking the number of 360, what the central angles add up to, and divide by 12. Okay. So the measure of the central angle, let me actually redraw it up here so we have something labeled. That's a little close. 360 divided by 12 is 30 degrees. So each central angle is 30. Okay. That means this part, which the apothem bisects the central angle, is half of it. So this is 15 degrees. And if that's 15, this is 75. And this is a right angle, by the way. Okay. So you can start working with that information that you have there now. Now we have, oh, by the way, if this is the segment, or if this is the, one side, half of that side is 9. So this little portion right there is 9. So I'm going to reconstruct that triangle for you, because that's a little difficult to see, and I guess this won't be drawn to scale, obviously. Let's actually flip it, so you're looking at it the same way. Flip left and right. Okay. So we're looking at something like this, where this is 18 degrees, obviously doesn't, or 15 degrees, obviously doesn't look like it. let's say it is. This is 75 degrees. This is a right angle, and this is 9 centimeters. Okay. To find the area, we have to find the apothem. We can find the perimeter already, by the way. Let's go and do that right now. Perimeter is 18 times 12. And 18 times 12 is 216 centimeters. And that's a perfect number. The apothem here, we're going to have to use, let's use the tangent function here. Let's take the tangent of one of these. Go tangent of 75. So tangent of 75 degrees is opposite over adjacent. So opposite of 75 is A over the adjacent, which is 9. I want my A and 9 to look the same. So A equals 9 times the tangent of 75 degrees. Okay. Tangent of 75, like I said, I'm going to leave that as is for now. It is, well, actually, here. Let's see what it is first. Yeah, I get about 33.59. But remember, I don't want to use that approximation when I find the area. So I'm going to use what I left in my calculator, which is 33.588455727. To do my 1/2 apothem times perimeter. So 1/2, 9 times tangent of 75 degrees times 216 apothem times perimeter. And that is about, so that divided by 2 times 216, I get about 3,627.55 square centimeters. Okay. So that's the area they found in this thing. Now, if you store it in your calculator and leave it here, it's 3267.553385. Because we're going to use this area here. If the area of a square is the same as the area of the regular dodecagon, then find the perimeter of the square, show all work. Okay, so the area of the square apparently is 3,627.55 square centimeters. Okay? Now the area of a square is taking your sides and squaring them. If I drew you a square here, areas on the inside, I do base times height. Now these are congruent. Oops. Okay, these are congruent sides all around. That's why we're just going to take one multiplied by the other, because these are right angles as well, by the way. So if I take a side and square it, side squared, S squared equals 3627.55. To find the length of one side, I have to take the square root of this. And the square root is about, I should put approximately, 60.23 centimeters. Okay, so that's the length of each side. The perimeter is taking all the sides and adding them up. Now all these are the same length, so I'm going to take that and multiply it by 4. And I get, I'll put 4s, I'll put p. The perimeter is about 240.92 centimeters. Okay, so again, I take the area, which is the same as the area of the dodecagon, they said. I take the square root to find the length of each side, multiply it by 4. And I get the perimeter of my square. If the area of a circle is the same as the area of the square, which is the same as the area of the dodecagon, 3627.55, then find the radius of the circle, show all work. So the area of the circle now is 3627.55. Those are 5s, by the way. Area of a circle is pi r squared. If I take pi and multiply it by the radius squared, then I get this, apparently. To solve for r here, we have to divide both sides by pi. This is an this is an instance where I'm okay with you taking approximation, or I'm not taking approximations, but not leaving this in terms of pi. I want to see what this actual number is. Take this over pi is r squared. So let me do that quickly. Let's do this. Let's divide this by 4 and then square it again. So 3627 divided by, there's a pi button on your calculator. Please don't use 3.14. Don't use approximations. We don't have to. So r squared is about 1,154.69. So r, square root of that is 33.98 centimeters. Okay, that's the radius of a circle whose area is that, which is the same as that as well. Okay. Number 4 is actually really quick. Look at the diagram of the Pentagon. So this is a pentagon, 5-sided shape. The dashed line is a line of symmetry. So a line of symmetry does mean that it reflects these guys over. So whatever we're looking at here, we're looking at here. Like these are congruent. But so are these angle measures, everything else. So as angle measures are congruent, then this is also 3x, this is also x, and this is also 110. So we're well on our way already. It's 110. Solve for x, then find all angles of the Pentagon show will work. Okay, D and C are 110 degrees. We're already set there. A pentagon has 3 triangles in it. All 3 triangles add up to 180, or each triangle adds up to 180. So 3 180-degree triangles is 540. So the sum of the measure of the interior angles is 540 degrees total. So that means if I take the measure of this angle, 3x plus 3x, which is 6x, plus the measure of this angle, x, plus the measure of this angle, 110, plus 110, plus this last one, x, that equals 540 degrees. Combine like terms, we get 6x plus x is 8x, plus 220, 110 plus 110 is 540. Subtract 220, you get 8x is 320. Divide by 8, you get x equals 40. So x is 40 degrees. So measure of angle E and B are also 40 degrees. And measure of angle A is 6x, so 6 times 40 is 240. So this is 240 degrees. Which, by the way, that looks kind of weird if you think about it. Now you can add these up and double check. 240 plus 40 is 280, 390, 500, 540. But this isn't drawn to scale, by the way. If you think about it, this is 90 degrees, this is 180, so 240 is another 60 degrees outward. So the 240 degrees looks like this. So this becomes not even an obtuse angle, it becomes an outward angle. So you're actually looking at a pentagon that looks probably more like this. Let's see. E is 40, so it probably looks more like, that's 110, like this, and then it goes in like that. Okay, that's okay to do. This is still a pentagon. It's still a pentagon. So, wink wink. Okay, 5 is kind of interesting. I hope it'll make sense when I talk about it, because I'm not there with you when I do. But Zoe the goat is tied by a rope that's 28 meters long. So these arrows indicate the rope. So one of these are 28 meters. Let's just go and draw all of them and look at this as we go. Of a 20 meter by 30 meter rectangular barn in the middle of a large grassy field. Alright, so that stuff not necessarily important. But if there's a goat, it can go out as far as this. So it can walk in whatever area this is. Let's find out which diagram makes most sense about Zoe's grazing area. Now these aren't drawn to scale, but we are talking about this being the shorter side, this being the longer side. So this is, so this is a 20 by 30 barn. 20, yeah. So 20 by 30 meter barn. And this is a 28 meter rope. So we're going to see which one makes most sense. If you can make the rope as straight as possible, 28 meters, and you start to go to the 20 meter area, like this one right here. I start to go around, and I'm gonna go right here. Should my rope be able to exceed 20 meters, and should I be able to wrap around the fence a little bit? Like, say the rope's going this way, and this way further. Now that I get to the edge of the fence, it's gonna tie, or barn, it's gonna tie against the barn. If I want to walk all the way over here, it would go like that. So that makes sense. Okay, that one works. This one here, 28, I go around it, here's 20, here's what's left, I can still go around. This one doesn't make sense though. I walk with a rope that's 28 meters long, I should be able to go past this 20 meter wall, barn wall. Here I can't, so this one's definitely out. This one is not representative of my diagram. So all those make sense from the 28 meter side. Now going the other side. If I go, yeah, I'm a goat, 28 meter rope, I shouldn't be able to get on the other side of the 30 meter thing. I shouldn't even reach the corner of the fence here. So this one's starting to make sense. Let's see if this one makes sense. 28 meters, I'm going around. Should I be able to go around the 30 meter fence with a 28 meter rope? Absolutely not. I should not be able to exceed that with my rope. So this one does not make sense. So the only one that makes sense here is this one for this goat diagram. It's the only one that can cover that amount. And the reason? Well, because 28 can exceed 20, but it can't exceed 30. So this one makes sense as far as what Zoe can do when she's grazing. Okay, find the area of the field Zoe can graze. Okay, this one's a little different in terms of you just need to make sure that you see what you're looking at here. Okay, this is not a perfect circle. In fact, it's not even a complete circle. But if I were to look at two circles here, here's what I'd do. Okay, see if you can make sense out of this. I have two circles that I'm looking at. First of all, this is a radius, if you think about that. If this was tied to a post, okay, if I had a circle right here, and here's a center, and here's a post, Zoe could walk all the way around, conceivably. In this case, Zoe's tied to the corner of the barn. And in the corner of the barn, Zoe's restricted by barn walls, and assume Zoe can't go inside the barn either. Say Zoe's on the outside in the grazing area. So this is the circle for that 28-meter radius. This is what Zoe could have been doing. But then the barn starts to restrict Zoe in these two parts. Say here. Whoa, that's big. Say here. Here. So Zoe's only able to cover this area in the big circle in grazing. Okay, so this is 3/4 of a circle, of a complete circle whose radius is 28 meters. Remember, this is still 28. It doesn't negate the fact this is 28. So if I find the area of this big circle, say area big, pi r squared, so pi times 28 squared, which is 700, what was that, 784? Yeah, 784 pi. That's square meters. So that's the area of the entire circle. That's including the non-shaded part. This entire thing is 784 pi. Now, I need to look at 3/4 of it, though. I need to look at this part. So I need to take 3/4 of 784. Pi. And that is 588 pi square meters. So the area of this shaded portion, the area of the green, is 588 pi. That's the grazing area Zoe can get until she's restricted by the walls. But we're not done. We still have this portion to take care of, to deal with. And imagine, I wish I could zoom in. There's probably a way, I just don't want to screw up. Imagine I'm looking at a circle here now. It's really small. Okay. Let's check this one out right here. This is here first I'm gonna draw the circle. So now I'm looking at this small circle here. Okay. What happened to Zoe here was she was on this rope. She starts going this way, and the rope, again, so this is her rope. She's going this way, and she starts to hit this corner. Okay. The rope hits the corner, and she can only start to now take her rope, whatever's left, and start grazing this way. The whole rope is 28. She gets restricted by a 20-meter wall. So 20 meters of her rope is right here. Remaining 8 is what's going out here. This is as far as she can get all the way around the center area. So if you look at the small blue circle, and I'm just going to go around it one more time. If you look at the small blue circle, I'm looking at a circle with a radius of 8 meters. Because this is the rope. Here's 20, so this must be 8. Okay, so if I'm looking at a radius of 8 meters here, I want to find the area of this circle. But what I'm going to find then is the area of only this sector, the part that covers this area. And this is 90 degrees and this is 1/4 of it, which is 90 degrees. But this is just 1/4 of the small circle. So what I'm going to do is I'm going to find the area of the entire small circle with a radius of 8. So that's pi times 8 squared. So that's 64 pi square meters. So the area of the small circle is 64 pi. I need to find the area of the blue part now, just 1/4 of it, 1/4 of it. So I'm going to take 1/4 of 64 pi, and that's 16 pi square meters. So the area of what Zoe can graze in total is the addition of the two, 588 pi plus 16 pi, which is 604 pi square meters. Okay, that's the total area she can cover. That approximates to 1,897.52 square meters. Okay, so your answer's up here. This I'll do it in red. Answer's up here, either the exact or approximated area there. So again, this isn't a full circle. It's taking these portions of your circles and adding them together. So you have to do a little perception, and then you have to do a little work. You have to make sure that you're following along with everything that you're doing as you go. Okay. Okay. Now moving on. Last one, number 6. A cookie baker has an automatic mixer that turns out a sheet of dough in the shape of a square that's 12 inches wide. So this entire thing is cookie dough. Whoops. Okay, so this imagine this entire thing is cookie dough. So it's a square, so 12 inches. So this is 12 by 12. Entire thing's cookie dough. Okay, not just the shaded stuff. The shaded stuff are the cookies that we're going to cut out using our little cookie cutter. It's like, you know, we're using a cookie cutter. The cookies that he's cutting has 3 inches of diameter, so the entire thing going through the center is 3 inches. If you get that, then half of 3 is 1.5, so its radius of each cookie is 1.5 inches. And this should make sense, because 3 times 4 is 12, so that should go out to 12 by 12, etc. So you have 16 cookies, by the way. The question is, too much dough is being wasted. He wants to find out what size cookie would have the least amount of waste. He's like, we should cut it into 2-inch cookies, or 5-inch cookies, or 16, or, you know, whatever. He's like, you're wasting too much cookie. Let's see how much dough is wasted. So imagine the entire thing's cookie. It's 12 by 12, which is 144 square inches of cookie dough. We're going to cut out the area of these 16. So let's find the area of one of them and multiply by 16. Area of cookies is 16 cookies times the area of each cookie. Pi times r squared. Your radius is 1.5. So that's 1.5 is squared is 2.25. 16 times 2.25 is 36. So you get 36 pi square inches of cookies that you have. The question is, what's the dough being wasted? So what's 144 minus 36 pi? This one's something I would prefer that you rounded. 144 minus 36 times, use the pi button. That's about 30 point, well, here. Let me do 36 pi first. 36 pi. Did you 144 minus? I just want to make sure I got the right number. Pi is okay. So 30.90 square inches of cookie dough is being wasted. By the way, for reference, 36 pi is about 113.10 square inches of cookie dough. So this plus this is 144. So this is how much cookie dough you get out of this entire thing. Oh, and by the way, this can work as a percentage. If I do 113.1 divided by 144, hang on, I do 113.1 divided by 144, and I get a decimal, 0.785. That means about 78.5% of my cookie dough was used. The rest, the 21.5% is being wasted. Okay, so this was the answer you're looking for, by the way, 30.9. 78.5 was being used. I was just giving you a good idea of how you use percentages. Wink. Okay, if the cookie cutter cuts 2-inch diameter circular cookies, then how much cookie dough would be wasted? So what they're saying now is, I'll just do this myself down here. If I make a new square, let's say it's still 12 by 12. Okay, now I'm going to make new cookies. They're all 2 inches each in diameter. So, I mean, this won't be perfect. It's probably not even close. So let me make it as close as I can. Say this is 2 inches in diameter. How many 2-inch diameter cookies could I fit in a row? Fit 1, 2, 3, and again, this isn't perfect. Say 4, 5, 6, right? 12 divided by 2 is 6. So I can get 6 cookies this way, and I can get 6 cookies downward as well. Okay? Because this is taking too long. 6 by 6. 6 by 6 is 36 cookies. So now I'm going to have 36 smaller cookies. So when I find the area of this entire thing, area of cookies, oh, by the way, if they're 2 inches in diameter, they're 1 inch in radius. That's 1 inch. Area of cookies is 36 times 36 cookies times the area of each cookie. Pi times radius, which is now 1 squared. 1 squared is 1. 1 times pi is pi. 36 times pi is 36 pi. So once again, we're left with 36 pi squared inches of cookies. Okay, just like this one. So the area that's going to be wasted is going to be this again. 144 minus 36 pi, which is again 30.90 square inches. So the supervisor said before, no, you're doing 36-inch, or you're doing 3-inch cookies. You're wasting too much dough. You're wasting, this much, or the cookie baker says, well, we're wasting this much dough, 30.9 square inches, which is a lot, I guess, because you can still make more cookies doing that. He says, make them smaller. Make them fit in more closely. He says, okay, I'm going to do it. Oh, we wasted the same exact amount of dough. So it didn't matter that we made them smaller or bigger. Let's try that again. Let's try it with the biggest possible cookie. Let's do a 12 by 12 area where we use a cookie cutter that cuts out this entire thing. I start right from the middle and I stem outward. Okay, let's make one big cookie. The diameter of this cookie is 12 inches. So the radius of the cookie, 6 inches. Okay, this radius is 6. Okay. Let's see if we waste the same amount, or if we use the same amount, therefore waste the same amount. I'm just do it right here. Area of cookie, it's 1 cookie, so just 1 times the area of the cookie. Pi times 6 squared. Okay, 6 squared is 36. 36 times pi is pi. 36 pi times 1 is 36 pi. So again, it's 36 pi square inches. No matter what we do, if we fit these cookies in exactly as we need to, the amount of space that's wasted will be the same, because we're still getting 36 pi, which is about this much cookie dough being used. This is how much is being wasted. Okay? And again, the way that the percentages work is you take the amount that you had and divide it by the total amount. Like even when we do sectors and such, we can get percentages of that. So if we waste 30.9, divide that by 144, because that's the total amount we have. 30.9 divided by 144, I did multiply. 30.9 divided by 144 is about 21.5%. Remember, that's 0.215. And if you've done decimals to percentages, you multiply by 100, because this is out of 1. Because 144 over 144 is 1. That's also 100%. So you multiply everything by 100 when you do it. So 0.215, 20.5. Okay. So wink, wink on the percentages, because those might help you there. Okay. And your last page is the backside. I want you to use this on my review video. To help yourself out when you're doing all these as well, because that'll just get you going in the long run with stuff like this. I hope this stuff helped you understanding how to do all these things here. If you have any questions, please ask in the thread, because this is good stuff.